Hello everyone, my name is Chatzimparmpas. I'm currently a postdoc at Northwestern University and I'm here to present our paper entitled HardVis, Visual Analytics to Handle Instance Hardness using Undersampling and Oversampling Techniques. This work is a collaboration with Fernando Paulovich from Eindhoven University of Technology and Andreas Kerren from Linnaeus and Linköping Universities. We will start with a brief discussion of the motivation for our work and the related research that we found. Then we describe the visual analytic workflow for performing undersampling and oversampling, which is also adopted by HardVis. Afterwards, we present the details with regard to the functionalities of the system, and at the same time we describe a use case with the goal of supporting the exploration of valuable sampling suggestions in a multi-class classification problem. Then we have the presentation of qualitative results of expert interviews we performed, which showed promising results. And finally, I will finish with a discussion of limitations and future work opportunities we identified. Let's continue with a brief explanation of what are instance hardness, data types, and sampling. Instance hardness refers to how easy or difficult it was for a machine learning model to classify an instance. Depending on the level of instance hardness, we separate them into 4 data types: safe, borderline, rare, and outliers. Sampling relates to either undersampling or oversampling techniques. The former remove instances from the training set, while the latter generates synthetic or artificial instances from the already existing data in order to balance the class distribution. The evaluation of the suggestions stemming from either undersampling or oversampling algorithms is the focus of our proposed system, HardVis. Despite the tremendous advances in machine learning, training with imbalanced data still poses challenges in many real-world applications. Among a series of diverse techniques to solve this problem, sampling algorithms are regarded as an efficient solution. However, the problem is more fundamental, with many works emphasizing the importance of instance hardness. This issue refers to the significance of managing unsafe or potentially noisy instances that are more likely to be misclassified and serve as the root cause of poor classification performance. There are several existing research works using automatic approaches for the identification of different types of instances and visualization methods for outlier and rare category detection, but not for the complete undersampling and oversampling procedure. Veronica is a domain-specific visual analytics system that uses undersampling and smooth for specific classes of data and groups of features. Despite that, HardVis accounts for instance hardness while enabling the micromanagement of the sampling techniques. WE is a tool that assists users in comprehending, interpreting, and selecting outliers identified by multiple algorithms. However, HardVis incorporates sampling mechanisms and enables the evaluation of the suggestions stemming from various sampling techniques. HardVis is a visual analytics system that enables the user to interact with the input data dynamically. It comprises the following workflow: explore various projections with alternative distributions of data types, leading to the division of training data into safe, borderline, rare, and outliers. In the undersampling or oversampling phase, tune the active algorithm's parameters to affect specific types of data. During the confirmation phase, identify which suggestions will impact negatively or positively the predictive performance and approve or reject any suggestion. And finally, store every manually operated sampling execution, identify confused test instances, and compare the predicted performance in each step of the process according to 2 validation metrics designed explicitly for imbalanced classification problems. All of these steps are iterative and they might occur in any sequence. The created knowledge obtained from the undersampled, oversampled dataset is the end result. The video demonstration presents a use case based on the vehicle silhouettes dataset. It showcases the main components of the system and the real-world application that shows how users are able to compare projections and distributions of data types and tune the sampling processes based on exploratory data analysis. In HardVis, each instance is sorted based on how easy or difficult it was to be classified using the k-nearest KNN algorithm. Both k-value of KNN and number of neighbors of UMAP parameters are automatically in complete sync in order to visually reflect upon the shifts in distributions of data types. Thus, starting with a default k-value of 5, the system progressively reaches up to 30 neighbors, leading to a grid of 9 alternative UMAP projections. Theoretically, the projection with the highest separate diagram correlation, SDC score, is the most trustworthy. However, a closer visual inspection is recommended to decide that. The stacked bar chart enables users to identify the percentage of each data type for the various nearest neighbors. Safe instances are color-encoded in light gray, borderline examples in gray, rare cases in dark gray, and outliers in black. In our application, we start by exploring which projection represents the data types in the best possible way. 3 projections reaching high enough SDC with minimum distance parameter equals to 0 are extremely content to observe anything. From the remaining projections, 2 of them have SDC score more than 83%. Although they are 2 similar projections, the last one clearly shows the difference between the bus and van classes in purple and orange respectively. Therefore, we choose to continue with this projection by selecting a number of neighbors parameter equal to 13. When we hover over the stacked bar chart, we observe that safe and borderline cases account for 47.16% and 34.54% of the training set, respectively. This is significantly different in the distributions of data created with lower values for number of neighbors. In summary, the visual analysis guides us in picking all aforementioned parameters. The panel on the upper left corner allows users to select the preferable undersampling or oversampling technique. Along with the standard parameters such as to which class the algorithm should be applied, HardVis can use any algorithm in a specific set of data types only. The outline of every circular point depicts the SBRO type an instance belongs to. Moreover, the deletion or addition of points is visualized with X and cross symbols respectively. On the one hand, the box plots enable users to compare all points versus their selection and even against the sampling suggestion. On the other hand, the table heatmap view presents for each instance the exact value per feature and the type column to emphasize on outliers first, rare cases then, borderline examples next, and finally safe samples. For all views, the values are normalized from 0 in dark brown to 1 in dark teal for the heatmap, and the features are ordered according to XGBoost feature importance. Additionally, the stacked and group bar chart constantly informs users about how the ratio of SBRO will change if the suggestions are approved. The polar chart uses similar encodings as the main projection, but it focuses on the diversion of every instance from the ground truth label, according to the predictive probability of the continuously retraining model. Lastly, the core diagram in the middle indicates the training confusion between all classes. At this phase, we want to deploy one-sided selection algorithm to undersample our dataset. As it can be seen, the seeds parameter requires some tuning since the algorithm removes solely instances from the minority class. The maximum available seeds value is a good candidate, but we observe that it's a bit conservative because more safe instances could be deleted in all classes, especially the bus class. By reducing this parameter in half, we become satisfied. However, there is an issue with rare cases being under consideration for removal by OSS. We further explore this group of points using a lasso selection and the table heatmap view to recognize why these instances differ from each other. 2 rather important features seem to be relatively different for the pink samples compared to the orange ones. The box plots could be of help for us too, especially when more instances are selected. We conclude that this diversity is essential for the model, and the choice of removing 3 out of the 7 selected instances can cause harm to the predictive capability in unseen test data. 4 outliers are also considered to be eliminated, however, only 1 is slightly problematic according to the polar chart. Hence, we decide to keep them intact. After our initial undersampling phase is over, we quickly try out another round of undersampling with the same strategy, but it appears to exclude many instances leading to negative results. Thus, we disable the algorithm and move forward. The default synthetic minority oversampling algorithm considers the whole training set when generating artificial instances. Nevertheless, numerous outliers are confusing for the model, which makes us think that SMODE should not take into account those points. Thus, we deactivate the outlier option from the menu and examine what will happen to the distribution of data types. Finally, we execute oversample to include the newly generated synthetic points in our training set. A history of previous actions is kept due to the Sankey diagram that registers users' manually executed sampling steps. The basic recorded steps are how the distributions of SBRO data types changes and from where instances were undersampled or oversampled after each core procedural action. The Sankey diagram reveals to us that several safe and then borderline instances were removed during the undersampling phase. The projection in the right corner highlights the confusing test instances based on the main projection, while the horizontal bar chart records the performance difference according to balanced accuracy and F1 score at every step of the process. Next, the projection related to the test set confusion highlights that 6 samples are actually cars but were predicted as buses. From steps 1 and 9 visible in the horizontal bar chart, the performance difference in each step suggests that using directly the sampling algorithms led to worse results. With the help of HardVis, the highest possible scores were reached in terms of balanced accuracy and F1 score. 5 machine learning experts evaluated HardVis in individual 1 hour and 15-minute interview sessions. The feedback was related to the following aspects: workflow, visualization and interaction, limitations. In summary, the provided feedback was encouraging and in favor of HardVis compared to employing automatic approaches. One of the experts concentrated on the problem of visualizing hundreds of features. He acknowledged that the box plots and the table heatmap view are interactive with zooming and panning functionalities, which could partially address this issue. Also, the feature importance could be useful for deciding which features are not informative for a provided dataset to exclude them beforehand. Another expert mentioned the issue of exploring more than 3 classes. Arguably, the main bottlenecks are the inverse polar chart and the extensive use of colors. The proposed visualization could be further improved to scale with more than 3 classes by using advanced HardVis-based approaches. Furthermore, he noted that multi-class classification problems could be resolved as being binary due to the one versus rest strategy. An expert proposed to deploy HardVis in a cloud server supporting parallel processing to improve further the efficiency of the system. 2 out of the 5 experts mentioned that heavily modifying our visual analytics system is inevitable in case we would like to extend it to other types of data. For example, image or NLP datasets that consist of non-interpretable features such as pixels and word vectors. However, they completely agree that this was not our original intention. Finally, another expert stated that non-expert users or even domain experts could find it difficult to operate HardVis and be advised by all visualizations concurrently, despite the views being logically positioned in a single window. Therefore, as an improvement of generalizability to other target groups, he proposed to separate the views in different tabs depending on the certain domain problem at hand and the user's prior experience to reduce the cognitive load. However, for machine learning experts, this deep level of granularity and the guidance received from the tool are necessary for making decisions. More details about the tool's limitations can be found in the paper. All in all, these limitations constitute possible directions for future work. Here are some final concluding remarks. In this work, we developed HardVis, a visual analytics system that uses manually configurable undersampling and oversampling techniques to handle instance hardness. As part of an intensive iterative process, multiple coordinated views assist users in defining an ideal distributions of data types, undersampling particular safe for removal samples, and oversampling others. Additionally, it facilitates the exploration of algorithmic suggestions using a variety of visual clues to confirm non-harmful removal or addition proposals. Finally, our visual analytics approach is ideal for dealing with the instance hardness and class imbalance challenges because it makes the entire process adjustable and more transparent. That was it from my side. Thank you all for your attention, and remember to visit the links below for accessing the paper, watching the demonstration video, and tweaking the code of HardVis.